We want to continue our look at chemistry by discussing the difference in a compound and a molecule. All right, let's start with a molecule, the smallest part of a compound that still has the properties. We might say a molecule of sodium, a molecule of hydrogen, a molecule of oxygen. We typically refer to a compound when we put together two or more elements and bond them. If we put together hydrogen with oxygen, if we put together sodium with chlorine, we would say this is a compound. You'll see in a lot of chemistry texts, biology texts, that these two terms are used interchangeably. They may say a molecule in one instance, a compound in the other, and be talking about the same thing. What you're looking at, however, is a chemical formula. This chemical formula tells you two things: what atoms we have and how many of them we have. So here is the chemical formula for table sugar, common sugar. You can see that it's made of carbon, hydrogen, and oxygen. It's actually made of 6 carbon, 12 hydrogen, and 6 oxygen. This is referred to as a subscript number. It is smaller than and placed to the lower right of the atomic symbol. Or here, 4 oxygen, yet notice there's no number written here with the phosphate. If there is no number, it is an understood 1. Because there's one of them, we don't have to write it. So for example, table salt. It's made of sodium and chlorine. How many? Well, there's no number at either. So there's 1 sodium and 1 chlorine. If we look at the chemical formula for water, we know that water is made of 2 hydrogen and 1 oxygen. 2 hydrogen molecules, 1 oxygen molecule can make the compound water. And what we've actually done is we've chemically bonded hydrogen and oxygen, or sodium and chlorine, to make this compound. Chemical bonding actually occurs between the electrons only in the outermost shell, those electrons that we looked at in that Bohr model. When we drew the Bohr model, the most important level was that valence, that outer electron shell, because those are the ones that are going to participate in our reaction, our process of forming a bond. Now, we can predict how reactions will occur by looking at the periodic table. So remember, we had families going this way, we had periods going this way. By looking at the placement on the periodic table, you can make a prediction before you ever do a chemical reaction. If there's an element here and an element here, and we want to react those together, well, they're close together horizontally. So they're going to have a very mild reaction. If we take an element from here and from here, they are further apart horizontally, and we would expect a much more vigorous reaction out of these elements. We can look at the different types of chemical bonds. The first one we'll look at is an ionic. Now, an ionic bond is when we transfer electrons. An ionic bond is when an atom has a number of valence electrons that it would like to transfer to another atom. Well, when we transfer electrons, we change the electrical charge of the atom. And when we do that, we create an ion, which is a charged particle. So if we go back to the Bohr models, and we want to look at sodium and chlorine, because we want to make sodium chloride, which is table salt. If we look at those Bohr models, we'll see that sodium has 1 valence electron, and chlorine has 7 valence electrons. Neither of these is stable. To be stable, the valence electron shell should have 8 or a multiple of 8. So sodium needs to donate or transfer this 1 electron to chlorine. That would cause sodium to lose this valence shell and go to this valence shell where we have 1, 2, 3, 4, 5, 6, 7, 8 electrons, therefore it would be stable. Chlorine would gain that 1 electron, giving it 8 electrons, therefore it too would be stable. Notice we went from 1, 2, 3 shells to 2. We maintained all 3 shells. The third one has 8 or multiples of 8. This is now chemically bonded together as sodium chloride. But notice that we've gone from being just plain Na to Na with a plus. So let's talk about why. If we go back to the beginning and look at the number of electrons we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. We also have 11 protons. Remember that protons are positive. So if I have 11 positive charges and I have 11 negative charges, that makes my atom neutral. If we look at chlorine, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 17 electrons and 17 protons. Again, that is neutral. Well, when we transfer an electron, this number goes down to 10. And this number increases to 18 because we have actually taken an electron and transferred it from one atom to the other. So now I have 10 pluses and I only have, 11 pluses, but I only have 10 minuses. So this cancels. When I get down here and look at the end, I've got an additional positive charge. Therefore, sodium is a positive ion. Chlorine has 1 more negative than it does positive charges. Therefore, it has become a negative ion. We call these ions because they are electrically charged particles. When you transfer an electron, when you lose or donate an electron, you will always become a positive ion. Try to think about it as donating or giving. It's always positive to give a gift. It's always positive to give your time. If you're giving an electron, you will become positive. If you give away 3 electrons, then you become a 3 positive. If you give away 2 electrons, if you give away 1 electron, if you gain, if you take, then you're going to become a negative ion. Why? Because you are gaining a negatively charged particle. If there is a number with this, such as 3 minus, that tells you how many electrons you gained when you formed this ionic bond. It's referred to as an ion. So remember, if we donate electrons, we're going to become positive. If we gain electrons, we're going to become a negative ion. The next type of bond is referred to as a covalent. Now, co means to be together. Think about cooperate, work together. Co-ed, boys and girls together. Co is to be together. A covalent bond occurs when 2 atoms share their electrons together. And in the process of sharing the electrons, they become stable. Now, sharing is represented slightly different. You'll notice that because these are sharing, we have taken their valence electron shells and we've overlapped them. And we're showing how many electrons we're sharing. In the case of hydrogen, they're going to share 2 electrons. Notice here at oxygen, we're going to share 4 electrons. Look at the sharing here. Carbon is sharing a pair with hydrogen. Carbon is sharing a pair with hydrogen. The number of pairs we share is represented in the line we draw. This is referred to as a single bond because it is one line we are sharing one pair that we can see there. So look how many pairs we're sharing in the next example. 1, 2 pairs of electrons. Therefore, you see 2 lines. This is called a double bond. So what kind of bond is this? Here, here, here. These are also single bonds, a pair of electrons being shared between carbon and hydrogen. By sharing these electrons, we have become stable. Now, when they share, they create something referred to as electronegativity, and attraction between electrons. And that's actually based on their number of protons. The more protons they have, the higher their electronegativity, the higher their attraction. This sharing can occur in 2 different ways. Now, think about 2 siblings sharing something. They're not always going to equally share something. The 2 types of sharing comes down to the equality. Is the sharing equal or is the sharing unequal? Well, in a non-polar bond, the atoms will share equally. Think about non-pole. Poles tend to be on opposite sides. These are not on opposite sides. They're going to share equally. Why? Because most often it's the same element sharing with itself. And you tend to share with yourself equally. Polar, think about being 2 opposite poles, 2 opposite sides, will form a covalent bond, but they're not going to equally share the electrons. One of the atoms is going to, let's say, hog the electrons. This usually occurs between atoms that are different. Hydrogen and oxygen are different, therefore their sharing is not going to be equal. This is referred to as a polar covalent bond. In this case, oxygen shares with oxygen, will do so equally. But in this case, oxygen will share with hydrogen, and because oxygen is a larger atom, it's going to command more time with the electrons, and it's not going to equally or fairly share the electrons. It's called a polar covalent bond. Now, there is a unique type of covalent bond called a hydrogen bond. So first thing to know is this is covalent. So if it is covalent bond, why do we give it a unique name? Because it is the covalent bond that only occurs within water. It's the bond between hydrogen and oxygen. Remember, this is a polar bond. Well, hydrogen bonds have some unique features. First of all, the way that hydrogen is attracted to that oxygen is really a weak attraction. It is weak, and therefore it is easily broken. Think about having 3 drops of water. Put 3 drops of water on your desk and take your finger and push the drops of water. You can very easily break apart the drops of water. Because it is a weak bond, instead of drawing it here with a solid line, we would draw it like this. The dotted line indicates weak and easily broken bonds. However, there's a flip side to this. If you put together many hydrogen bonds together and united, they can be exceptionally strong. Think about the damage a wall of water can do. A wall of water can knock a building down, but yet you can take your finger and pierce through a drop of water. So alone, hydrogen bonds are very weak, but if we put them together, they can be strong. This hydrogen bonding gives water some very unique properties. So we need to look at water. Very important, because all living things are anywhere from 70 to upwards of 90% water. So what's the importance of water? It is our universal solvent. Well, it has some unique characteristics. One, water has a really high heat capacity, meaning that water can absorb tons of heat without even having a real change in temperature. Your best experience with this is to boil a pot of water. Think about putting a pot of water on the stove and stand and try to wait on it to boil staring at it. It takes forever. because water can absorb a large volume of heat before it ever changes a single degree in temperature. This is a benefit to living things because we can go out, we can absorb tons of heat, and because our body is mostly water, we can absorb all of that heat without actually changing our body temperature. It helps us maintain normal internal temperatures in spite of great changes in the weather outside. Second characteristic, water has a really high heat of vaporization. Talking about sitting there waiting on that pot of water to boil, it takes a lot of heat to actually cause the water molecules to break those many hydrogen bonds together and evaporate the water. But we use that to our benefit because we use it to allow us to get rid of excess body heat. You have water on your skin, i.e. sweat, and you go outside and the heat evaporates that sweat. Well, it takes a lot of energy to evaporate that water. Therefore, as the water evaporates, it pulls away that excessive body heat with it. It allows any animal to cool itself. All right, water is a solvent. Matter of fact, water is our universal solvent. It facilitates all the chemical reactions that occur inside of a living thing. Well, all of our solutions consist of two parts. The solvent, which typically is water, and a solute, what we are dissolving into that. So let's work through a few examples so you can get used to these terms. Let's consider making, say, Kool-Aid. You have a cup of sugar, you have your Kool-Aid pack, and you have a container of water. In that case, what is the solvent? Your solvent would be the water. So what is your solute? The sugar as well as the Kool-Aid pack would be your solute. We're going to dissolve the sugar, dissolve the Kool-Aid pack into the water. And you'll see just about every example you can sit and think about, water is going to be your solvent. Now, when you're looking at solvents, we also see certain characteristics occur. We see that our polar compounds, those that have that unequal sharing of our electrons, tend to be hydrophilic. Hydro means water. Philic means to like or to love. In other words, polar compounds easily attract water. Whereas nonpolar, where our sharing was equal, they tend to be hydrophobic. They fear water. They cannot attract water. For example, oil would be a hydrophobic compound. All right, so we know that water has a high heat capacity. It can absorb tons and tons and tons of heat without ever changing temperature. It has a high heat of vaporization because it does absorb so much heat. When it does evaporate, it helps remove heat from the body. We know that water is a universal solvent. We know that water also has properties referred to as being cohesive and adhesive. Now, cohesive is to cling or hold to each other. So when you're talking about being cohesive, remember co means to be together. This is where water is holding to water. Water is holding to water. Whereas adhesive, think about adhesive products like tape. That means to be sticky or to stick. Adhesive is water sticking to something else. So if you look out on a window after it's rained and you see droplets of water clinging to the window, that is adhesion. The water clinging to the window is adhesion. But if you sit and look at it, you'll notice that two drops of water really close together will pull together. That is the attraction between the two water molecules pulling together. That is cohesion. We need both cohesion and adhesion to pull water through any tube. Easiest example is to think about drinking through a straw. When you drink through a straw and stop drinking, you'll notice there are a few droplets of whatever you're drinking clinging to the side of the straw. That is adhesion. But what actually allows the fluid to be drawn up the tube, it's not only the fact that it will cling to the side of the straw, but that the liquid will cling to itself. That allows plants to bring fluid up, draw water up into the plant. It allows animals to move blood around in their blood vessels. The fact that the water sticks to the water, cohesion, and that the water sticks to the vessel wall, adhesion. We also see that water has a really high surface tension, meaning at the surface, water molecules cling together tighter than they do below the surface. It gives kind of a skin to the water so that small non-polar objects can actually sit on top of the water, like little water strider insects. This is the principle you're using when you want to skip a rock. The key is you can't break the surface if you want to skip the rock. At the surface, they're going to cling together. You can allow the rock to kind of skip along. But if you ever break the surface of water, the rock's going to drop. We also see that the last property of water, if it is frozen, it is less dense than when it is in a liquid state. Because as it freezes and changes from a liquid to a solid, it changes and increases its size. Therefore, if the volume increases, it becomes less dense. Now, this is a benefit because objects that are less dense can float on top of objects that are more dense. So if it's frozen, that means it will float on top of something more dense like the liquid. Your ice cubes will float. If you put a single ice cube in a cup, it will float on the top. It is less dense. That allows frozen environments to have an insulative blanket on the top. That ice on the top of a pond is an insulator that protects the organisms underneath it from the temperature changes going on in the environment. That insulator allows organisms to live throughout winters. Imagine if the exact opposite property were true. If frozen water was more dense, then the water on the surface would freeze, sink to the bottom. The next layer would freeze, sink to the bottom. And over the course of a winter, the pond would freeze completely top to bottom. Therefore, every living organism in that pond would die. We also know that then as the ice melts, it draws heat from the environment, prevents those sudden changes in temperature, and allows the things to live throughout the fluctuations of temperature changes. So water has a high heat capacity. It has a high heat of vaporization. It's our universal solvent. It's cohesive and adhesive. It clings to itself and vessel walls. Water has a high surface tension, and we know that frozen water is less dense. We also need to consider in chemistry properties called acids and bases. Now, an acid is any substance that when you put it in water, breaks apart and rids itself of hydrogen ions. When you drop it in water, it's going to break apart, release hydrogen ions. How do I know that's an ion? Because I see the positive. Just think back what that means. If there's a positive sign, hydrogen has transferred an electron to another molecule. By losing an electron, it became a positive ion. Acids have certain characteristics. One of them is taste. Now, you would never taste a substance to tell if it's an acid or a base because that could be harmful. But acids do tend to have sour taste. Lemon juice is an acid. Vinegar, coffee, those are acids. Bases will take up that hydrogen ion or release hydroxide. Now notice hydroxide is a negative ion, indicating it has accepted an electron. Now bases have different characteristics. Taste-wise, they're bitter. If you don't know what bitter tastes like, go get a can of Hershey's Cocoa like you would bake with and stick your finger in it and taste it. It does not taste like a Hershey's Kiss. It doesn't have the sugar to it. It is bitter. Quinine, tonic water is bitter. Bases also tend to be soapy. If you stick your finger in a base, it's going to feel soapy. Shampoo, Windex, those are all bases. But if we can't really taste them, and we shouldn't dip our fingers in them because that could be toxic, then how would we measure it? Well, we use something called a pH scale. A pH scale can be tested using papers that test the chemistry of the solution. And it runs from 0 to 14. where 7 in the middle is neutral. And any number less than 7 is an acid, and any number greater than 7 is a base, which is more commonly referred to in chemistry as being an alkaline. Now, this scale takes some explanation because it's not simply a 1-point scale, meaning from 7 to 8 is 1. It is logarithmic, which means it's going to be multiplied in units of 10. So every time we change from one to the other, from 7 to 8, that's multiplied by 10. 8 is 10 times stronger than 7. If I go up to 9, that's another multiple of 10. So from 7 to 9 is 10 times 10. That's 100 times different. Something with a pH of 9 is 100 times stronger than something with a pH of 7. So little changes in pH are big problems. For example, in the human body, 7's neutral, our blood ranges about 7.4. But you can get to, say, 7.8. Seems like a very small change, and it will kill you. Why does this little change make such a big difference? Because remember, this is a logarithmic scale. From 7 to 8 is by a multiple of 10. So if this little change is such a big problem to living things, what do we do to prevent these changes? We use things called buffers. Buffers are chemicals that we can add to substances to help keep the pH within a normal limit. Your cells are very, very sensitive. Therefore, your body has the ability to buffer your solutions. Think about having a battery, car battery, and your car battery terminals are all corroded with acid. Now, how many of you have heard of someone taking a Coke and pouring on that battery cable to clean it? Well, chemistry-wise, think about what you're doing. There is acid on this battery cable, and there is acid in this Coke. Now, will it clean the terminal? Yes. But have you neutralized it? Have you buffered it? No, because you've added an acid to an acid. All you've done is let one acid eat another acid. It would be much better if you had your corroded battery terminal to take Windex and squirt on your battery terminal. Why? Because this is an acid. And if I use the opposite, which is a base, we have actually buffered it. We have neutralized the acid, which will help clear the problem for a longer period of time. If you look at the pH scale, where here is our neutral, you can look for some common things that you may be familiar with. Soda, beer, vinegar, very acidic. Lemon juice, stomach acid. Look at oven cleaner. Too often we think about, oh, strong acids can burn me. They can eat away my skin. Well, strong bases can do the same. Anytime you get far away from neutral on either direction, it is excessively harmful. Oven cleaner has huge warnings on it. Wear gloves, wear thick rubber. Oven cleaner can eat your skin away just like hydrochloric acid. Anytime you venture away from that 7, it can be very harmful to be on the strong end of either side of this. So in our chemistry chapter, over 2 lectures, we've looked at atoms. We have looked at how to look at the structure of an atom, a Bohr model. We've looked at the difference in molecule and compounds, knowing that most likely they're interchangeable terms. We looked at our chemical bonding, particularly ionic, where we've transferred electrons, and covalent, where we're going to share them. And we talked about a special hydrogen bond, a special covalent bond, hydrogen bonding, that gives water its unique properties. And then lastly, we looked at determining acid versus bases.